Ice protection. So I'll start with a bit of a disclaimer. What's wrong with this picture? There's no propellers. I'm building on one of Mark's back slides. I'm not sure why he chose a Boeing for a background, but hey, we'll go with it. So if you know Mr. Madison, this is so. But propeller ice protection. So why do we have it? Flying into icing conditions. For aircraft, in order for them to be for it to be legal to fly into known icing conditions, they have to comply with FAR 23.2540. Now this was replaced in about 2017. There was a previous FAR, and I don't remember the number that used to be there, that was much more detailed. But if we look at that FAR, if I pull it up, so you can see it. You can see it's a very, very short one. And it's basically all it says is the ice protection system has to provide for safe operation. And then the airplane also has to have an autopilot that will automatically sense a stall and kick off if it starts to stall because of icing. Now that doesn't deal with the propeller, but this is it. The old FAR had like full on details of what this actually meant. But they changed it to this and essentially said whoever builds the airplane, part 23 is aircraft construction for general category aircraft. It has to do that. Now it does reference part 25, and in part 25, that's where what icing conditions are actually like they're laid out. But that's for transport category aircraft. So kind of the assumption nowadays is there's not a lot of non-transport category aircraft that can fly into icing conditions. Is there a question? No. Okay. So it's really hard nowadays to get a small plane certified to fly into icing. But it doesn't mean that builders or companies don't put de-icing or ice protection equipment on their aircraft. We have an aircraft here that has ice protection equipment, actually a couple of our aircraft. But the Cirrus fleet, for example, we have one Cirrus here. Anyone familiar with it? Anyone seen it around? We have an SR-22 that has, you'll see it has silver leading edges on the wings, and it's not certified for icing conditions, but it has this anti-icing stuff on it in case a pilot gets caught in icing conditions by accident. They can use it to essentially get out. So ice protection has to provide for safe operation, continued safe operation, and then it has to, prevent the airplane from stalling if it's on autopilot when ice starts to form. So that's where I was talking about our SR-22 being constructed with ice prevention or ice protection. It's not actually certified to fly into known icing conditions. But if an operator inadvertently finds themselves in icing conditions, they can use this these anti-ice systems in order to get out. The other thing is we have to be able to detect if an aircraft is, part of this safe. It really wasn't laid out in the FAR, but we have to provide for safe operation. A big part of that is we have to be able to detect ice formation in the first place. And so there are different ways of detecting it, and then it has to be managed. So reasons we got to be careful of it, or it has to be taken into account when you're looking at these. We have things like frost before takeoff. We can get potential ice accumulation or even snow. Okay, that's going to add weight and reduce aerodynamic lift. And so we can't have that forming on there. Now propellers, that's not such a big deal, right? Because they're usually on the ground. What we're most worried about are those horizontal surfaces, the wings and the horizontal stabilizers. So you're really not going to get a lot of propeller ice formation on the ground. But in the air, in flight, it does the same thing. Even small amounts of ice or thin layers can add a significant amount of weight. And it builds up on those leading edges and any exposed areas, and it can disrupt the airflow. So it can affect the lift of the wings, And on the propeller, it can affect the amount of thrust that your propeller produces. Right? It can screw up that airfoil. The other thing we have to worry about is on propeller airplanes is that ice can disrupt airflow in a couple different ways. One is if it forms over those intake inlet areas, and again, that's more of an airframe de-icing thing. But if we allow ice to form on the propeller and it's spinning at high speeds, what's it going to potentially eventually do? What's the biggest force that a propeller is subject to? Centrifugal force. So if you have ice building up, what do you think is going to happen? It won't tear off the prop typically, but the ice will shed in large chunks. It'll get big enough and heavy enough that that ice that's forming there will be enough centrifugal force on it that it will eventually overcome its bond to the propeller and it'll go flying. And you don't want that to get sucked into an engine. It'll also hit the side of the plane. If you go out to our King Air sometime, look at the top of the nose. The propellers are in line with the nose. It looks like a golf ball. And that's from where the propellers sling ice against the fuselage. Question? It does work that way. When we get to de-icing, you'll see how that kind of plays out. So yeah, the ice that forms more in the middle is less likely to shed than the ice that's out by the tips of the propeller. Okay, it will potentially all shed eventually. Oh, another thing we get is evaporative icing, and so when if there's moisture on the aircraft as it's moving, that's going to increase the evaporation. And so if there's any water or vapor in there, that can also potentially condense and solidify. And so that can restrict airflow into areas, or we have a lot of air movement over the prop. So we start to get things that look like this. So here is icing that forms on a spinner on the left. And on the spinner, oftentimes, that's not such a big deal. Right? We're not really worried too much about the airflow of the spinner, other than it can potentially shed. In fact, when I worked on turboprop, we'd get these come in. Sometimes you would have ice on the spinner that you could actually grab it and pop it off, and it was like a bowl. It formed a mold of the shape of the spinner, and we would pop it off. Now, if that sheds, it does have the potential to get sucked into the engine inlet if the engine inlet is somewhere near the propeller. The other thing they would get is actually sometimes they'd come in and there would be like an icicle spike off the front of the propeller. Those are pretty cool. We sometimes get ones that were 1.5 feet long or so. And again, if they're attached, not a big deal. If they shed, they have the potential, then where's that going to go when it sheds? It's going to go back, and it's going to hit what? What's right behind the propeller spinner? The propeller itself. So it's part of that. The prop blades hit it, gets slung into the side of the fuselage. So like I mentioned, the King Air out there, you go look at the nose of it, look at the top of the nose, and it looks like a golf ball. The two turboprop aircraft I worked on, their propellers were about in line with the second row of seats or so. Row 2 in both airplanes, didn't have a window because the windows were weaker. And then the one airplane I had it had no window. The Saab 340 doesn't have a window in row 2. And we had a second piece of aluminum that would basically be double-sided taped to the side of the airplane. It was a sacrificial skin layer. And every so often we'd peel that off in like a C-check, and we'd inspect the area underneath, because there would be ice that would hit it. It was 60 thousandths thick. Ice would hit it hard enough to dent the skin underneath it. We'd have to fix that and then put a new sacrificial layer on the outside. You also get glazing, so that's glazing there, and then you can get glazing on your leading edge, and it starts to look something like that. What's that going to do right there on the right? What do you think the big issue with that right there? That is going to have a major disruption in the airflow above and below, or in front of and behind the propeller. And so that's what we're trying to prevent. So the first thing that crew has to be able to do is to detect ice. Do you think we can see ice forming on the propeller? Not typically. So how do you think we can perform visual detection? Observation of parts of the aircraft that can be seen. What areas might the pilots be able to see that ice could build up? Yeah. The cowling. Okay, areas of the cowling. And then I heard someone else say something. The outside of the cowling? That can be. Certain areas might actually, because you got air coming in the front before it gets hot, right? In a pressure cowl. Yeah, the front lip, like the leading edge of the cowling where the air can flow in. You could potentially get some ice buildup. I think I heard someone say wings as well. Your wings are going to be a big area for ice buildup. The windshield itself is another common area that'll ice up. So you'll have that. In order to see it, though, you'll need some kind of a lighting source. So you don't think of lights being part of ice protection, but you have to have ice lights. We had lights on our airplanes that pointed at the leading edges of the wing. And that way the crew could flip those on to look. And that's one way they would know to turn on their ice protection systems. But it's limited. We can only do the areas of the aircraft that the pilot can see, right? And especially as the aircraft gets bigger, it gets harder and harder to see areas of the aircraft. Have any of you sat in the King Air and tried to look at the wings, like what you can see on the wing? They're pretty easy to see, but as you even get into like a 30-passenger turboprop, if you sit in the flight deck cockpit, look back, you can maybe see the outboard, maybe quarter of the wing. It's really hard to see in where the engines are. King Air's still on Jackson there, I believe. Yeah. Other ways we can do it is instrument ice detection. So larger twin engine, typically twin engine aircraft, typically turboprops, are going to employ an ice detector system. And these are on any kind of jets pretty much. So this is more of an airframe component. But again, so icing in general is we're detecting the icing, whether it's for wings or for engines, for inlets, or for propellers, right? We're just detecting icing. We want to prevent it from building up in any of those areas. But what we have with an ice detector instrument is there's a sensing element. In its simplest form, it's a sensing element and a heater. And so that sensing element sticks out into the airstream. And anything that sticks out into the airstream, anything that's disrupting the flow of air, is going to be prone to having ice buildup on it. Okay? Pitot probes, they're prone to ice buildup. Leading edges of wings and stabilizers are prone to ice buildup. Inlets for engines are prone to ice buildup. The propeller's prone to ice buildup. Right? Even things like lights that stick out tend to build up ice more than smooth, flat surfaces. So what we do is take a little probe, we stick it out into the airstream, and that's the spot where ice is going to want to build up. And that probe is vibrated. It has everything has a resonant frequency. Who can describe a resonant frequency? What's that mean? Learned about it in physics. Has anyone seen a resonant frequency? Anyone seen a resonant frequency in action? So we take our ice detector probe element that's out in the airstream and we vibrate it. We put a little, they use a piezoelectric crystal, and don't worry about that for now. But it's vibrated at a certain frequency, which is the natural frequency of this probe, and it's about yay big. Little piece of metal sticking out like that. And it's an ultrasonic vibration. You can't like hear it. You can't even touch it. You don't even really feel it. It's a very small vibration. But then what happens though is as that's flying, as the plane's flying, if ice builds up, it builds up on the end of that little probe. And when you change the mass or the amount of material in that, its resonant frequency changes. And so when that frequency changes, the ice detector can sense that change in vibration, how fast that's vibrating. And it tells it that there's ice there. Now the heater then you don't want ice to build up, and then you need to know when it stops icing. Maybe you just flew through a small area of moisture or a cloud or something. So then a probe, a heater cycles on, warms that up, melts any ice that's built up on it. It shuts off again, and then it checks to see if it gets ice buildup a second time. So here's what these probes look like. This one, top left here, the only thing I don't like this picture, it does have a little cap. The red part's just a little protective cap that's over top of it. You can see the bottom where it shows the entire body of this thing. So the part that's out in the airstream, this lower wing shape part, that's just a strut to kind of hold the probe out a little further. The probe is this little metal piece on the end. And so you can imagine as ice builds up on that, it'll change how fast it's vibrating. Tell the plane that there is ice forming. Tell the crew that there's ice forming. They're very small. They're deceiving. We would test them, go up and grab them, and see if the ice trigger light would come on. What do you think happens if you grab them too long, though? What do they do? What do they do to get rid of the ice? They get hot real fast. So we'd kind of grab them to get them to activate, but you wouldn't want to hold them very long. They get hot enough to burn you. So they're also right for me about head height. So when I'd stand up from underneath the airplane, that strut there was a metal piece about yay big, perfect height to gouge my forehead wide open. So, but well, it wouldn't burn if you hit it. This edge right here, back here, is very sharp. See that corner? You stand up, rake that thing over the back of your head. Doesn't feel good. Okay. So so you can do it visually, or bigger airplanes are going to have these ice detectors, and some will have one on each side. Again, you can see more of a jet picture here, but there are turboprops and larger twins that might use these. It's another object, something else that has weight and height, or weight and all that. So once we detect the ice, then we've got to deal with it on the propellers. And there's two main ways that ice gets dealt with on the propeller. One is anti-icing, and anti-icing is done using chemical means. So some aircraft use a chemical anti-ice system. The other way is to prevent ice buildup from happening. It can be, I have de-ice, thermoelectric de-ice, and that is an ice removal thing. So rather than preventing it from building up, we're going to melt off ice as it forms. Okay. So starting with anti-icing system, these are commonly known as TKS systems. If you want to know TKS, there's TKS written out. Sure, whatever the heck that means. Tecumseh, Kilfrost, Sheepbridge, Stokes. Not quite sure. System. Not sure where it comes from, but the goal here, what we want to do is TKS is a fluid-based system. It's a chemical fluid, and those fluids are designed to lower the freezing point of water. That's one thing they'll do. So it's a chemical reaction. It changes the properties of the water. The second is it's a physical property where it helps to prevent ice from bonding. So essentially, how does it make it difficult for ice to stick? You know, if I say it's the mechanical properties and makes ice prevent from stick, what's the kind of the simple way of saying that? Nope. We melt it by changing the freezing point. That's a chemical change. So this one here makes it difficult to stick. It makes the surface slippery. It makes the surface slippery or slick. Okay? So it puts a coating, it puts like a gel coating on the airframe or on the propeller that is very slippery. And the areas you'll see typically is the wings, horizontal and vertical stabilizer. These are going to use something called wheat panels. Okay? They're basically, this is what if you look at the Cirrus or SF-22 out here, the metal leading edges are not actually solid. They have micro holes. They're actually laser drilled holes. They punch little holes with a laser. They're too small to see. And they pump fluid on the backside, and the fluid weeps out. And then it goes over the airstream pushes it over the wing from the leading edge to the trailing edge. Okay. Propellers use something called a fluid slinger. if we can get fluid to the center of the propeller, what's going to move it out along the blades? Centrifugal force. So we're going to use centrifugal force to our advantage here. And then windscreens use nozzles. They'll spray right at the bottom of the windscreen, and then the wind's going to carry it up from the base up. But on our propellers, we're going to use a fluid slinger system. So when they're installed in the aircraft, you're going to have some reservoirs. Typically one, some aircraft have two. There's going to be pumps to distribute this, or pumps, and then they're going to distribute it through hoses to those weeping wings on the leading edges, to the windshield nozzles, and then to our propeller slinger is the device that's going to get it out onto the blades. And what we use, there's a few different common chemicals used in this. The first one's isopropyl alcohol. Okay. That one's probably the oldest, least often used nowadays. Same thing with methyl alcohol. So a couple alcohols. Alcohols are really good at lowering the freezing point, but they aren't very slick, right? You felt, different rubbing alcohol, that kind of thing. They aren't super slick. The most common today is ethylene glycol. What is ethylene glycol? It's antifreeze. It's an antifreeze derivative. Ethylene glycol is the active ingredient in antifreeze. So this is like an antifreeze. It's technically a liquid, but it's a real thick, viscous liquid, almost a gel kind of. Okay, so it's not like the antifreeze that's in your car, or not like the antifreeze that goes in an engine that's purely a liquid. This is a very thick, trying to think, it's got the consistency probably of, yeah, okay. Yeah, it is actually mucus-y consistency, I guess. Not quite as disgusting as what comes out of my kids' noses when they're sick. It is gross. It gets all over everything. When one of these planes operates these systems and it comes back, it is everywhere, and it will be dripping off the plane for probably the next week. Okay, this stuff takes forever to drip off, and it'll be dripping out of the wings. When I used to work on jets that had this down at Duncan, we'd pull their hawkers, we'd pull the hawkers inside, and we'd basically put a strip of pig mats underneath the leading edges. It would take about a week for those to stop dripping all over. What else do you have to be worried about? As a maintenance technician working around this, what do you have to be very careful of in this situation? If it drips on you, and that's such a big deal. What are our hangar floors typically made of? Concrete and oftentimes epoxied floors. What do you think they are like when you get this ethylene glycol coating them? This stuff is slicker. This is probably makes floors the slipperiest that they can ever be. So if you're working around these, you got to be careful with it. It is gross when it gets on you, but it lowers the freezing point of water. It makes it difficult for the ice to stick, and it is antifreeze based. So if we look at just the propeller components, here are those components kind of as they're hooked up. So this is showing a twin engine aircraft configuration. We've got our fluid tank, and these fluid tanks are typically accessible inside the airplane. So this is a tank-based system. What does that mean for this system to operate when the aircraft's running? How long is the system going to operate? As long as there's fluid in the tank, right? Compare this to some other aircraft, some other systems we'll talk about later are electrical systems, or in your systems class, you'll talk about bleed air systems. How long will those systems run? That'll run as long as the airplane's operating. So this system will only run as long as there's fluid in the tank. Oftentimes these tanks have a fill port on the inside where the crew can actually carry jugs of this stuff and fill up in flight if they're going to be in extended icing conditions. But you have your fluid tank, you have a pump and it sends it out. There's a nozzle at the end that goes into something called the slinger ring, and we'll look at that. And the slinger ring has the ability to, using centrifugal force, bring the fluid out to the blades. So if you look at that closer, it looks something like this. So the slinger ring and the nozzle, here's our fluid supply with a little nozzle on the end. That's stationary, right? This is connected to, this fluid supply from the pump is connected to the engine. typically, or in the cowling area. And the slinger ring is connected to the propeller. That's spinning with the propeller there. So fluid is sprayed into the slinger ring, and then as this is spinning, centrifugal force is going to pull it down these discharge tubes, and it's going to come out. And which edge of the propeller do you think it's going to go to? It's going to the leading edge of the propeller so that it works its way back. So if we look at actual versions of it, here is a slinger ring. On the left is the front side of it. So the prop would be mounted here, and here are those discharge tubes that would be kind of routed to the front. And on the back, here's the back plate. It also, you'll hear it called a propeller back plate, a spinner plate, or a spinner ring. Okay? This is what the spinner is attached to. In lab, you've all removed a spinner at this point, right? Okay. So this is built into that ring that the spinner screws to. You can see the nut plates around the outside where the spinner would attach. And here, this little lip right here is the slinger ring. So on the engine, there'd be a little nozzle spraying or sending fluid in this ring right here. And that's what those tubes are attached to when you get to the front side. When it's installed and a spinner's over it, you'll see something that looks like this. And you can see the discharge tubes just kind of peeking out there near the leading edge, and that will get fluid down. Now, where is the majority of the fluid going to be? At the root or the tip of the blade? Root, tip, root. Majority of the fluid is going to be at the root here, right? It's coming out here. It's coming in there first. So this goes back to who asked the question about tip versus, yeah. So at the ice is less likely to form and build up at the tips. Okay, the further you are on the propeller, if ice does build up, it's going to shed earlier at the tips and further out because that's moving faster. There's more centrifugal force out there. And because it doesn't build up as much before it sheds, it's lighter and it's less dangerous. Okay? Whereas the stuff that's more inboard tends to be the thicker buildup, and when it does finally shed, it's more dangerous. Okay? So by having these on the inboard part, first of all, it just works. The physics of it works by having them near the root of the blade. But the other part is it's going to provide the most protection near the root of the blade where the highest danger would occur if ice were to be building up. The other main system we have for ice protection is electrothermal de-icing. So now instead of trying to prevent the ice, prevent it from, the chemical stuff, the TKS fluid, that chemically prevented ice from forming, and by making the surfaces slippery, it prevented the ice from adhering to the surface. Now we're just going to try to get rid of ice. We're going to allow a certain amount to build up, and then we're going to get rid of it. So for this, we have boots installed on the airfoil, but these are not, you've probably, in airframes, have you talked about de-ice boots? Have you seen de-ice boots yet for wings and that kind of thing? Those are pneumatic, they inflate. The de-ice boots that are used on here are electric, so they're electric heating elements. We take wires, we take a couple pieces of rubber, and we run wires between them. We sandwich a bunch of wire between, and then when we run current through it, that wire acts as a resistor and it heats up. We stick those to the leading edge of the propeller near the root. So they're bonded to the blades. They're basically, most of them nowadays are just a sticker. They have the adhesive pre-attached to them. And you clean the propeller. The blades have to be very clean before you apply them, and then once they're applied, they kind of stick down to the surface. And if they go bad, if you get a short in them, or if the wires get broken, they stop working, they have to be peeled off. You have to clean the contact area really good, typically using things like MEK or other kind of glue type strippers, and then reapply a new boot that doesn't have the problems. We have to be able to get electricity to them. So we have devices called slip rings and brush blocks that are going to transfer electricity out to them from the stationary engine cowling to the rotating propeller. These are operated by timer systems. And then you also have ammeters for indication, and then the wiring and various electrical components that go into it. So when we install it all together, it roughly looks like this. So we have our propeller here with some boots on the leading edges, a back plate that has slip rings on it. There's going to be a brush block installed here up on the top of the engine. And then here's our timer, kind of just showing the timer can be anywhere. But if you look at what these look like on an actual propeller, here's our boots. And you can see they're only bonded to the root area of the blade. They're only, in this case, about the first third of the blade. Okay. And again, that's because the area outside of that, anywhere from this boot outboard toward the tips, is fairly low concern. And again, because the centrifugal force is much higher there than it is at the root, the ice there is going to shed before it gets large enough to really cause much damage. Or it's not even going to really be able to build up much in the first place. But this first third of the blade is our critical area where it's spinning slow enough that the ice can really form, and form to the point where the chunks get big enough that when they break off, they can cause damage. Or before they break off, it can so severely disrupt the airflow that it decreases the efficiency of the propeller. And each of these boots, so there's three boots here, depending on the size of the propeller, the size of the aircraft, they may have one or they may have two different heating elements inside of them. And so when they're laid out, if you have a single element, if I draw my, if this is a boot, you can actually go up to these and you can see wires running through them. And so there'll be a wire that comes out here, and then you can see it just kind of weave back and forth like this, all the way down the length of the blade. So that's a single element boot. When you have bigger boots, sometimes these use a lot of current. All of these use a lot of current. And if you have a larger boot, you can run into a situation where a single element would draw too much current. And not just a single element, but anytime these are running, they're all going to be running at the same time. Why would we heat all three at the same time? Why don't we cycle them? What would happen if we cycled them? You'd have weight distribution issues, right? You'd have one blade would be lighter than the other. So all three have to heat at the same time. So not only is it one de-ice boot that uses a fair amount of current, but all of them, these are run in parallel with each other. So in this case, you would have three de-ice boots that are all wired in parallel. Okay. What happens when you wire things in parallel? It draws a lot more current, right? Parallel increases the current, series increases the, it splits the voltage across them, but the current stays the same. In this case, they're going to use a lot of current. So if we have three and they're larger, when all three of them are powered, they may pull too much current. So what we'll have is a three-wire boot. So it will have a common terminal here in the middle. And essentially, it'll have a coil going towards, say, this is the outboard end. It'll have a second coil that does the inboard end, like that. And so what happens here is instead of powering the entire boot at the same time, this center one's always going to be the neutral, the ground. This one always goes to ground. We can apply power to this side first to heat the outboard half. And then, remember I said these are run by a timer? Then once we've run the outboard half for a certain period of time, we shut off power here, and now the timer directs power to the inboard half. And we heat the inboard half. But it's going to be all three blades. So all three inboard halves would be heating at the same time. And then all three outboard halves would be heating at the same time. And then all 3 inboard halves would be heating at the same time, and all 3 outboard halves would be heating at the same time. So that's where you have a single or dual element per boot, and kind of the wires running through and how they're done. But the neutral is the one that kind of comes off the middle. The ground is always going to be off the middle. When you have like this, it really doesn't matter which way current flows through it, because it just heats up. You run current through and it heats up. So if you have one of these single element boots, you have to have 2 wires going to the prop, or 2 electrical connections to the propeller. We're almost out of time, aren't we? Okay, well, we'll have to finish this another time. So why don't we leave off there, and I'll finish this up on next week.